let's set up a checklist for sketching the graph of a function f of x. So, first item, we're going to want to do all things we can do without taking a derivative. So first, you'll want to get your domain under control. Once you know all points where your function's defined, we can look for discontinuities. So if we have jump discontinuities or vertical asymptotes, we're going to want to note these. Okay, if I have regions of increasing and decreasing, concave up, concave down, our vertical asymptotes and discontinuities are going to break those regions. Okay, next, once the domain's under control, we can start trying to do some basic sketching. So one thing I can do, I can look for zeros of my function, or I may want to plot a few points just to get an idea of what's happening on all the different regions in the domain. Once we've done that, we'll want to know about behavior as we go to plus infinity or minus infinity in x. So that's just going to be taking your limits as you go off to plus or minus infinity. That will give us horizontal asymptotes or behavior shooting up to plus or minus infinity in y. So that's all we can do without a derivative. Next point, let's see what we can do with the first derivative. So, compute the first derivative. First thing I'll do is look for critical points. So these will be points where the first derivative is equal to 0 or undefined. The first derivative is equal to 0, it's going to be a horizontal tangent line. If the first derivative is undefined, that can mean a few things. It definitely means there's no tangent line at our point. But we could wind up with things like vertical tangent lines or tangent lines from the left and from the right that don't agree. In any case, we're going to take all of our critical points, take our domain, mark off where the critical points are, and then that gets us to our next step. So regions increasing and decreasing. Once we've carved up the domain with the critical points and the discontinuities, we'll want to check one point in each region against the first derivative. If the first derivative is positive, we'll have a region of increasing. If it's negative, we'll have a region of decreasing. That's everything I can do with the first derivative. Okay, we'll compute our second derivative. That's just the derivative of the first derivative. Now, same idea. We're going to look for all points where the second derivative is 0 or undefined. We'll take the domain. We'll mark up all those points, all the points where we have discontinuities. We check a point in each region, put the second derivative on each of those points, and then if we get a positive number, we have concave up. A negative number means concave down. That's everything we can do with the second derivative. Let's look at an example. So let's consider f of x equal to 1 over x minus 2 squared. First, we get the domain under control. For a rational function, the domain is just going to be all points where the denominator is non-zero. So here, our domain is going to be all x except for 2. At x equal to 2, we have a vertical asymptote. So that's going to be a discontinuity. So whenever I consider increasing or decreasing, concave up, concave down, that discontinuity splits our regions. Okay, that's everything we can do with the domain. Next, let's look for zeros. So our numerator is equal to 1, so there's no way that this function can be equal to 0. Of course, I could plot a few points just to get an idea of what is happening for later on. So why don't we use x equal to 0, x equal to 3. If I put 0 in there, I'm going to get 1/4, so I'll plot that point. If I put 3 in there, I'm going to get f of x equal to 1. So that's going to be this point. Okay, what's left? We can check the limit as our function goes off to plus infinity, minus infinity in x. So we're looking at 1 over x minus 2 squared. If I expand that, we'll see that the lead term in the denominator is an x squared. So what will happen? If I go to plus or minus infinity, we're looking at 1 over term going off to plus or minus infinity. So that's going to go to 0 on both sides. So we'll have a horizontal asymptote on the left and on the right going out to 0. Okay, we see this. That's going down like that. This is coming down like this. That's everything we can do without the first derivative. So we move to our second point. Compute our first derivative. So in this case, what do? We rewrite the function as x minus 2 to the minus 2. Bring the minus 2 down. Subtract 1 off the exponent. Leave the inside alone. Chain rule says you multiply by derivative of the inside. So that's just going to be a 1. So our first derivative is just minus 2 over x minus 2 cubed. Note, no critical points here. Okay, we can never have f prime equal to 0. The numerator is equal to minus 2. And if we look for undefined, we're going to have it at the point x equals 2, but that's where the vertical asymptote is. So it's already accounted for. Now, if we want regions of increasing and decreasing, we'll have to check a point on each side of x equal to 2. So why don't we check x equals 0, x equal to 3. If I put 0 in here, we get a negative over a negative, which is a positive. So note, we don't worry about the number. We're mostly just interested in the sign. So it's positive, which means we're increasing on this region. If I put 3 in there, what comes out? We're going to get a negative over a positive, which is negative. So we're going to be decreasing on this side. That's everything I can do with the first derivative. Let's move to point 3, the second derivative. Second derivative, again, we're going to use the chain rule. So minus 3 comes down. That gives us a 6 in front. X minus 2 stays as it is. Exponent goes to minus 4. Derivative of the inside is 1. So I have 6 over x minus 2 raised to the 4th power. Okay, there are going to be no points where the second derivative is equal to 0 or undefined. Okay, we can never get 0 because the numerator is 6. And then, if you note, if we're going to divide by 0, we're going to have x equal to 2, and that's where the vertical asymptote is. So we already know about that. Now, we could check a point on each side, but if you note, I have 6, which is positive, over x minus 2 to the 4th power. That's always going to be 0 or positive. And if I'm not at the vertical asymptote, it's always positive. So our function's always concave up. Now what to do is connect the dots. So let's take a look at what's happening. On this side of the asymptote, we're increasing and concave up. So we're having our horizontal asymptote at 0. So it's going to come in from 0, increase and concave up to our point, and then we got to match it up to our vertical asymptote. So that's going to look like that on the left-hand side. On the right-hand side, same idea. We're decreasing concave up. I'm going to come down from the vertical asymptote, go through our point, and then this is going to go off to our horizontal asymptote on the right of 0. So that's what the picture of our graph looks like.